Hello students, a very warm welcome to today's class. We are about to step into one of the most fascinating worlds of mathematics, differential equations. Let me start with a question. Have you noticed how your hot cup of tea cools down quickly at first, then more slowly later? Or how a small colony of bacteria in science class suddenly becomes a whole population in a few hours? Or how your 1,000 rupees in the bank somehow keeps growing on its own? All these changes, temperature, population, money, are not static. They evolve continuously with time. And mathematics has a tool to capture this continuous change, the differential equation. For example, we may write it as dy by dx equals g of x. That small expression is the mathematical diary of change. Now, let's get specific. Think of a normal algebraic equation. X squared minus 3x plus 3 equals 0. Simple, it only involves the variable x. But now, imagine we include a derivative. Consider dy by dx plus y divided by x equals 0. Notice the difference? We now have the dependent variable y, the independent variable x, and the derivative dy by dx. That's the essence of a differential equation. An equation that contains one or more derivatives of a dependent variable with respect to its independent variable. So while algebraic equations capture positions, differential equations capture movement, the heartbeat of mathematics. Differential equations come in two big families. Family 1, ordinary differential equations or ODEs. They involve derivatives with respect to just one independent variable. For example, d squared y by dx squared plus dy by dx equals 0. Only x is the independent variable, so it is ordinary. Family 2, partial differential equations or PDEs. They involve derivatives with respect to more than one independent variable. For example, del squared z by del x squared plus del squared z by del y squared equals 0. In class 12, we'll stick to ordinary differential equations. Don't worry, partial differential equations are like the Avengers of mathematics. They'll come later in physics and engineering. Now comes the concept of order. Order means the order of the highest derivative present in the equation. Let's test this with examples. Example 1. dy by dx equals e raised to the power x. The highest derivative is first order, so the order is 1. Example 2. d squared y by dx squared plus y equals 0. Here, the highest derivative is second order, so order is 2. Example 3. d cubed y by dx cubed plus x squared into d squared y by dx squared equals 0. The highest derivative is third order, so order is 3. So the rule is simple. The bigger the derivative, the bigger the order. Now for degree, the often confused sibling of order. Degree is defined only if the equation is a polynomial in derivatives. That means derivatives like y dash, y double dash, and so on should appear in simple powers, not inside sine, cosine, or logarithm. Example 1. Bracket d squared y by dx squared close bracket raised to power 2 plus y equals 0. Here, the highest derivative is second order, and its power is 2. So order is 2. Degree is 2. Example 2. Y double dash plus bracket y dash squared equals 0. The highest derivative is second order, with power 1. So order is 2. Degree is 1. Example 3. Sine of y dash plus y equals 0. Here, y dash is inside a sine function, not polynomial. So degree is not defined. Golden rule. First check polynomial condition. If yes, degree exists. If no, degree is undefined. Let's solve one step by step. Take y double dash plus y dash raised to power 3 plus y equals 0. Step 1. The highest derivative is y double dash, which is d squared y by dx squared. That makes the order equal to 2. Step 2. Check if it is polynomial in derivatives. Yes, y dash cubed is polynomial, and y double dash has power 1. Step 3. So degree equals 1. Final answer. Order equals 2. degree equals 1. And that's how you carefully analyze order and degree. Now, why are differential equations so important? Because they are everywhere. Population growth, differential equations. Radioactive decay in chemistry, differential equations. Motion of planets, again, differential equations. Even your money in compound interest or the cooling of tea in thermodynamics, all modeled using differential equations. Solutions are not just numbers. A general solution has arbitrary constants describing a whole family of curves. A particular solution fixes those constants with initial conditions, like saying y equals 1 when x equals 0. So here's the recap. A differential equation is an equation involving derivatives. Order is the highest derivative present. Degree is the power of that derivative, but only if the equation is polynomial. And solutions can be general or particular. And that's our exciting start to differential equations. In the next class, we'll continue to explore basic concepts with more tricks, examples, and applications. Until then, keep observing change in the world, because mathematics is how we capture it.